So today we're going to finish up the chapter. We're going to start with calorimetry. Oh yeah. Pass your worksheet or your stuff up and I'll pick it up. Correct.
Next week?
Oh wait.
That's awesome.
Okay, calorimetry is problem-solving approaches to heat transfer, and so what you have is a system, and usually it's filled with water because you know the specific heat of water, and you have you'll have an initial temperature. You'll know how much water is in here. You'll know, and you'll measure the change in temperature of the water, and and you can find the initial temperature of an object. Then it's called a calorimeter. It has a vacuum. Well, good calorimeters have a vacuum in here so that it's not much heat loss to the outside. The one we're going to use is not a vacuum, but it still is pretty good.
Wait, we're going to use one?
Yeah. Mm-hmm. Yep, that's what the lab will be. So we can ignore the heat gained or lost by the cup because it's small. So we look at the heat gained by the water because the temperature of the water will rise is equal to the heat lost by the hot object. Or you can even do it the other way. If you have ice or something really cold, you can look at the heat gain or lost by the water is equal to the heat gained by the ice or the cold object. But you're using positive heat values. You aren't going to use negative. Even though it's lost, you don't use negative for these equations.
What's that container called?
Calorimeter. So in a student's experiment, this is how we're going to use it. We're going to, what's the equation for heat?
QMCAT?
Mm-hmm. That one, yep. So if in a student's experiment, a 0.125 kilogram metal ball is placed in a calorimeter filled with 0.150 kilograms of water at 21 degrees Celsius. The initial temperature of the ball is 98.5 degrees Celsius. After reaching equilibrium, the temperature is 27.3 degrees Celsius. Find the specific heat capacity of the metal. So our heat gain and our heat is equal to our heat loss. So we can say the heat gained by the water is equal to the heat lost by the metal. So we'll have the mass of the water is 0.150 kilogram times, what was the specific heat of water?
0.8.
It's 4.186, I think. It's not that far.
Yeah. There it is.
4.186 times 10 to the third.
I knew it was 4. I knew there was a decimal. What? No, what did you say? Caitlin, do that. Keep your notes on paper. Again with the scientific notation.
Okay, this really bothers you, doesn't it?
Scientific notation is useless.
Okay, that's enough. What's the change in temperature of the water?
What are we looking for?
What's the change in temperature of the water? It starts out at 21 degrees Celsius. What's its final?
23, 47.3.
So 6.3 degrees.
Okay. So that's the heat gained
So that's
times the heat loss would be the mass of the metal ball,
was that QW or QN?
QW.
Okay.
And we're trying to find the specific heat of the metal. So I'm going to leave C there. And what's its change in temperature?
6.3.
No.
That goes from.
The initial temperature of the ball is 98.5.
Alright. 71.
71.2. Give or take.
Okay, so what's the specific heat?
What's 8 minus 7?
Miss Thaver, do you have a guess?
Do I have a guess?
Yeah, what's your guess?
I have no idea. 1,624.
444.5.
444.5.
Yeah. Just right.
That's joules per kilogram degrees Celsius. Okay, and then we're supposed to use the table to determine the type of metal. So does anyone have these printed off?
I do.
Ooh, what page is this?
I've iPadded.
Here. Let's look at the page on here.
What? I don't know where this chapter is at. I couldn't find it.
Chapter 9.
I have my notes printed out.
We'll look at the table. It's got to be towards the end of the chapter.
What table?
Table 3 or figure 3.2.
Okay, what do you want?
Which one is close to 444?
Like,
Iron.
There's nothing close to 400.
Iron.
Iron's the closest, yeah.
That's 10 to the second.
Well, yeah.
448.
So I think it's probably iron then.
Now it's on Edgemodo, yeah.
This is why we use scientific notation.
Questions on how to do a calorimetry problem?
Yeah, calorimetry is my new best friend.
Very close to iron.
Why did you see? Can you not tell that this one?
How about ooh, we don't have. Why don't we do U4 on my right, do the top one, and U4 on the left, do the bottom one.
Those guys. Alright.
Hey, you.
Alright. Well, we got 0.5 for the mass.
Point two.
since temperature goes up for water, I put the final minus initial because we just want positive numbers. We don't want negatives. And for this one, since the initial was higher, I just subtracted it that way. That way we don't have to worry about negatives.
I don't know if you guys do that. I know that.
Oh yeah, I think that's called practice after we. Oh, that has to come after practice. Yeah.
Yeah, wait for
So you divide the 1552, then you would multiply through, right? So then, oh shoot, what's that? So I have 134.86.
Basically, remember when you put participation bands on the rubric?
It didn't say that.
It
Did not.
says if you go in the back of the lab without permission, you will lose participation bands.
It's just the font looked like that.
There wasn't even a dot above the I. It just said pants. That's the best moment of my life.
You're so down when we talking about that.
Okay, so here's the water side. And this is equal to 115 minus TF. Right? So how would you solve now?
And my favorite band member was in physics. When basically
You'd add TF over 1 TF. So does that make 135.86 TF is equal to add 130. I added the 1 TF over. So 2027, is that what that is? 2022. 2.87 plus 115. 2,100, 137.87. So what's TF? You divide by 135. 15.74.
Oh, buddy, 74.
They got part of it.
They got 74.
Does that make sense though? So water started at 15, but the final temperature is 15.74.
Whoa.
So the water heated up because the transfer.
Right, because the zinc started at 115 and then it cools all the way down to 15.74. Does that make sense?
Zinc is weak. This water is so big.
The zinc specific heat was 388 compared to the 4,186. So it takes a lot more energy to raise up the 1 kilogram of water, 1 degree.
How much water you have compared to your zinc?
And you have a lot more water compared to zinc. So it should be a lot closer to the water temperature.
Yeah, you have 40 grams. You have 500 grams of water.
Yeah.
Your water is definitely.
So then, second group, you guys you say 45 degrees?
45.
Okay, and they both have water. Both samples are water, so they were able to use the same specific heat.
Is that right?
When you add
Is that the right answer? Do you know?
Let's see.
best of year round and then worst of all.
You just took the average. Oh, because the mass is exactly the same too. Yeah, that would work. If the mass wasn't exactly the same, you can't just average. Okay, latent heat.
Are you recording?
Yeah, should we just stop and you guys can have your assignment or what?
No.
Okay. Okay.
Are we recording?
Latent heat is heat gained or lost during a phase change. So I'm pretty sure in honors chemistry we did this. But when substances melt, freeze, boil, condense, or sublime, the temperature does not change during the phase change, but all the energy you're still pumping energy into it, it's all going to change the state of the molecules. And then once they are all in the same phase, then the extra energy getting pumped in is going to change the temperature. So you have a graph that looks kind of like this, where it goes like this. Where in this part we have solid. So you're raising the temperature. You're going to use our Q equation. This is temperature time. Here you're going to be melting, and we're going to look at the latent heat of melting, and we're going to use a different equation here. This is when it's a liquid, you will use our Q is equal to, here the substance is boiling, so we're going to use the latent heat of fusion, latent heat of vaporization here. Yes. There is a latent heat of sublimation.
What is sublime?
Right, it goes from solid directly to gas.
What if you have a line? What if you have a line in a submarine that's subliming to a gas?
Let's see what this says.
Visual concept. Whoa.
Miss Cleaver, did you hear my question?
Yep, and I'm ignoring it.
Why?
A phase change of a substance is its physical change from one state, solid, liquid, or gas, to another at constant temperature and pressures. In this example, the substance is water. Consider 10 grams of ice. The beginning temperature of the ice is -25 degrees Celsius. The ice is heated steadily. Its temperature rises until it reaches a temperature of 0 degrees Celsius. At this point, despite the fact that energy is continuously added, there is no change in temperature. The ice begins to melt and change into water at 0 degrees Celsius. Latent heat is present at this point. It is the energy per unit mass that is absorbed by the ice during its phase change from solid to liquid. When all ice has turned into water, the water's temperature increases steadily from 0 degrees Celsius to 100 degrees Celsius. At 100 degrees Celsius, the water's temperature stops rising and the water turns into steam. Once again, latent heat is present. It is the energy per unit mass that is absorbed by the water. When the water has completely vaporized, the temperature of the steam continues to increase. Thermal energy continues to be absorbed.
Okay. Yeah.
The bottom graph was time, and that takes such a long time to get all the water. Right?
hmm Well, in this case, they use actually heat instead of time. Be the same. But yeah, it takes so much heat. So heat of fusion, and this book calls it L sub F. Last year, I think we used delta HF. What's your heat of fusion? But it's the heat required to melt 1 kilogram of a substance. It's also the heat released when 1 kilogram freezes. So whenever you go from a solid to a liquid or a liquid to a solid, you'd use the same heat of fusion. And which segment represents that? That process? B. So it'd be right here. Maybe right here.
I bet you there's going to be a little question.
The heat of vaporization is the heat required to change 1 kilogram of substance from a liquid to a gas or gas to a liquid. So which segment represents that? D, because it's water to steam. Yep. We have all these different values for latent heat of fusion and latent heat of vaporization. I'm sure that's in your books because you may need that for some problems. But suppose you are camping in the mountains and you need to melt 1.5 kilograms of snow at 0 degrees Celsius and heat it to be 70 degrees Celsius to make hot cocoa. How much heat would be needed? Well, snow is at which phase?
I don't know. Solid, right?
It's a solid. And so, what was the latent heat for vaporization or for water? Latent heat fusion. Right here. 3. That's the specific heat. We want the latent heat of fusion. Is this number? 3.33 times 10 to the 5th. Oops. Is it degrees Celsius? Latent heat of fusion. Kilogram. So that's just how much energy is it going to take to change this 1.5 kilograms of snow into liquid water. So you're going to, you can use it as a conversion factor, or you can use it as equation. I prefer using conversion. So yeah, you have 3.33 times 10 to the 5th joules per kilogram. That way your kilograms cancel. You multiply it and
You get 4.995 times 10 to the 5th. I did that in scientific communication. Sacrifice.
okay, so now everything, it takes that much energy to change everything from a solid to a liquid. And now we're going to heat that liquid up to 70 degrees Celsius. This is where you're going to use your Q, MC delta T. So the mass of our snow is 1.5 kilograms. That's where the 4186 comes into play.
I thought it was 1.4.
Yeah, well, it was on the one previous, yeah. And then our change in temperature would be 70.
That gives you 4.3953.
Your afternoon announcements. Juniors and seniors, the
So to get total, you need to add them together.
Be sure to sign up in the counseling center if you're interested. Congratulations to
What was
the
it?
Junior High Band for being one of the 18 schools from across the state recognized for excellence in academic achievement by the Nebraska State Bandmasters Association. To earn this award, the cumulative average for the entire band had to be 3.5 or higher. Great job. Reminder, cheer practice for girls trying out for